You might be able to see that.
Oh, how pretty. Kids and I are over here right now.
Go down over it.
Second week of August. So we'll be there. Yeah, last year I didn't go. The year before I went briefly. So it's been a while. So halfway through, I'm going to go to Rome for about 2 weeks. Meeting some friends. We're renting a house outside of Rome. It's going to be awesome. Then we come back to Spain for a few weeks.
I'm good.
You guys like something?
Yeah. Take your time. Between Ashburn and Waynesville.
This is actually just slightly below because I guess the middle. They're obviously an i7 processor.
It's not like it's including the.
All right.
Chris, you're good? You can go off the laptop.
I'll just do a screen thing. It says.
All right. Okay, Chris, you're pretty much ready?
Yeah.
Okay. So
Yeah.
let's go ahead and get started. Welcome everybody. Glad you could all be here this morning in kind of beginning of the middle of the summer. Today, Chris Zarzar is going to present his master's thesis defense. And Chris has been with us for a couple of years now. He was his undergraduate at UNC Nashville. And he's been working very hard on lots of things, and he sort of narrowed it down to the half hour or so I'm going to tell you about today. And the title of his talk is A Precipitation Organization Climatology for North Carolina Development and GIS-based Analysis. And I'll turn it over to Chris.
All right. Thank you. And thank you to my committee and for Dr. Gaeta visiting us from Spain today. I'll jump right in. We got a bit to cover. But I first want to start out and preface by saying I like water, and I hope you do too, because it's pretty important. We use water in a lot of different ways. It's a great outdoors recreation resource. We use it for things like aesthetically pleasing functions, but also it's very important because the hazards associated with water, like flooding or ice storms, can cause serious implications. And with that, also, water is pretty important because it stains life and property. I'd say that's probably the most important, is the fact that we need it to grow crops and we need it to survive every day, like right now. So, we need to better understand water processes so that we can better know how to manage and mitigate water. And in this work, what we're going to do to better understand this whole cycle and this whole lifeline of water is we're going to look at precipitation, and we're going to look at how stream flow responds to precipitation. There we go. And starting out with the precipitation side of things, we're looking at four main mechanisms that can kick off precipitation, essentially. The first is mid-latitude cyclones. These are systems that we see on weather maps all the time. They've got a cold front and a warm front typically. And they are one of the primary drivers of wintertime precipitation because these fronts can cause lift that allows the air to go up, condense, and then we have rainfall. Another big player in precipitation, especially for coastal states, are tropical cyclones. Dr. Pratt and Dr. Nelson found out that these can actually contribute anywhere from 8 to 20% of precipitation to a region, depending on how close it is to the coast. Another one that's pretty interesting are something called sea breezes. And these are very typical for the Carolinas region. It's this boundary that develops along the coastline typically in the summertime evening when we have cooler ocean temperatures and really warm land surface temperatures. That creates a boundary and lift inland, and it forces airflow from the ocean over land that can cause lift and condensation and therefore precipitation. And we see that in this animation right here. This is the sea breeze coming right off the the ocean and causing lift and line convection. And the last kind of mechanism we look at here are surface characteristics. Things like topography, the orientation of a steep slope, if it is facing a prevailing wind, and that prevailing wind has to go up, which condenses and causes precipitation, and things like land use. This was heavily studied by Dr. Marshall Shepard, where he finds that precipitation is enhanced downwind of urban city centers. Why is that? Well, he finds that it's because the heating causes lift, and just like all these other processes, condensation and precipitation, and also that aerosols and the pollutants from urban city centers act as condensation nuclei, to which rainfall and water vapor can attach to, and then precipitate. Precipitation is enhanced. So all these mechanisms, they cause different characteristics in rainfall. And there's two main characteristics we want to focus on in our work here. And those include, I showed the other few, but those include, the main ones are mesoscale precipitation features and isolated storms. We've all had experience with these here. These mesoscale precipitation features are typically elongated features, and we know them, the most notable orientation or structure of them are these squall lines that we get here a lot. Those are those long elongated precipitation features that have a lot of heavy and strong winds with them initially, and then it's followed by persistent hours of rainfall. Whereas the contrasting type of precipitation feature are isolated storms. These isolated storms are much more localized, and it's common to pretty much what we're going to be getting today. It's these pop-up storms that last for maybe 30 minutes to an hour and then die off. But in those 30 minutes, they can cause some significant or substantial precipitation because they are very intense at a very localized area. And getting into more detail on how we actually define these two features in this study, mesoscale precipitation features. Simply, they're just features where the precipitation, the contiguous areas of precipitation exceed a length of 100 kilometers. Now, some people do define it further as an MCS. They like to do this because there are subsets of MPFs called the mesoscale convective systems. The only difference is those actually have, they're convective in origin, and they're known to cause severe weather and some serious implications for society, and that's why they've been so well studied. Something that has not been very well studied are isolated storms. And the reason for that is people really didn't think that isolated storms contributed that much to a region's total precipitation. However, Dr. Rickenbach and Rutledge, and also Rickenbach et al., found that isolated storms do make a pretty significant contribution. In some regions, it's anywhere from 10 to 12%, and actually more recently they found that it can be up to 60% for some regions during some seasons. And a quick look at what these look like on radar. This is your, this actually is as of yesterday, I believe. This is your MPF. It's elongated, and there's raining pixels right next to each other. And these are your isolated systems down here. We have this tiny little pixel area, this feature right here, one here, and one here. And so you can already see that there's very different looks to these systems. So with these different mechanisms, and with these different characteristics caused by these mechanisms, we come to that there's actual seasonal differences in precipitation regimes. In the winter time, when we have more mid-latitude cyclones, that means that we have more mid-latitude cyclone, we have more synaptically driven precipitation. And as Dr. Fieta found, that is typically associated with MPFs, or these larger, long-scale, elongated precipitation features. In the summertime, that synaptically driven precipitation drops to 30%. And so we wind up having more thermodynamically driven precipitation. And in this case, those are actually those isolated features. So the short-lived features that are smaller than 100 kilometers. Having these two seasonal, well, actually just having these different seasonal regimes and characteristics of precipitation, as can be seen here, where MPF dominate in the winter, and then in the summer, it's more split evenly. Isolated MPF have the same contribution for some areas. Well, having these different characteristics, seasonal characteristics, what's that mean for regional hydrology? And that's something that hasn't been touched on quite as much, and we're trying to do here. We want to see, do these different seasonal characteristics in the precipitation affect regional hydrology? And to do that, we're going to zoom in a bit more on North Carolina because we need to get a finer scale to actually assess this. And in North Carolina, it's very nicely split up already by the NC Division of Water Quality into 17 river basins. And now what a river basin is just a defined boundary where if any water falls in this boundary, it will go to one main river. For example, any water or precipitation that falls within the Neuse boundary will find its way to the Neuse River and discharge into the Sound. And these are just kind of examples of what the different areas of North Carolina look like. We have our mountainous regions here, and then we progress to more flatter terrains and then more open water terrains and sandier soils. And so the motivation behind the study is foremost, we need water to live. So it's essential to society. Then second is that we need a better understanding of watershed discharge response to precipitation. We know a good bit about watershed characteristics and how it affects discharge, but not so much about how different seasonal precipitation regimes affect watersheds, and more so how those affect different watersheds across a single state. And our state that we're focusing on is North Carolina. It's a unique study region because it has a variety of weather phenomena that impacts it from tropical cyclones to blizzards. Also, it has a variety of land characteristics, as I showed you in those previous pictures. And the last is that it is essential to precipitation is essential to water replenishment in the state. We don't have any major rivers. We don't have the Colorado or the Mississippi that run through the state. And so we rely on that precipitation to replenish our stream networks and our aquifers. So this brings me to my main research questions. And those are, how do precipitation modes of organization vary across North Carolina, both regionally and seasonally? And that's just looking at precipitation. But touching a bit on hydrology is, how do variations in frequency, in the frequency and distribution of these seasonal differences in the precipitation modes of organization, so those different rain features, how do those differences affect the regional hydrology across the state of North Carolina? And to do this, we're going to have to use radar data. Radar data is really nice because it's really high resolution, and we all have actually seen what radar data looks like, because a lot of us actually look at it every single day. This is a fine example of the National Mosaic Radar right now. And already we can see some features that I've been talking about. We can see NPFs, some isolated features right here off the coast, and then another NPF here associated with the frontal boundary. And so first thing I need to touch on is, how is that image created? Well, this explains it right here. These are over 150 NextRad radar sites across the country. And all of this data goes to one place, that's NCDC. And what they do is they navigate all of the data to a single reference, single spatial reference, so that then we can mosaic together and look at it all together like we do. Oops. And what we are doing in this study is we're taking these radar sites within the red box. We're taking 4 years of data, 2009 to 2012, and we're using that merged data to analyze and pick out NPFs versus isolated. And what we're looking at here is Hurricane Irene. And this is a nice example of what our data looks like when we have that merged data across the southeastern region. And so to make this, NCDC does this thing over there. They merge that data for us. They send it over to us with some of the precipitation, some quantitative precipitation information in there. And then once we get it here at ECU, we have an IDL program, and we've made this motor delivery algorithm that actually goes in and picks out what an NPF is and what an isolated storm is. And that's what is shown here. We look at these different rain features here. Each one has an ID, each of these pixels at really high resolution, so each 1 kilometer grid box has a precipitation ID. The algorithm goes in and it decides if these different precipitation boxes, if they are next to another precipitation box, we'll call it a contiguous feature, and if that exceeds 100 kilometers, it will go into the NPF category. On the other hand, if they are not contiguous features and they do not exceed 100 kilometers, it goes right into the isolated storms category. It's a pretty simple way of doing it, so it does actually work. And so we're looking at a couple images from the data set after we separate between these two modes of delivery. And this image is the seasonal composites, all 4 years data, 2009 to 2012. And it is separated by MPF, and then we'll see here in a second, isolated. And already off the bat, what we see are some seasonal differences in the mesoscale precipitation features. In the winter, in the winter and spring actually is when most of that rain is coming from MPFs. And in the winter, it's enhanced over the Ohio Valley and in the Deep South, the same thing with the spring. And in the summer, it's a very different story. We actually lose that enhancement in the Ohio Valley and the Deep South. And actually, MPF, while there's less MPF overall, it's enhanced off the coast. In contrast, with isolated precipitation, there's a minimum in the winter, which makes sense. That's typically synoptic scale-driven precipitation, so not the thermodynamic isolated precipitation. However, when we get more heating in the summertime, that's when we have the majority of our isolated precipitation, and more so it's along the coastal regions overland. So that's where we're seeing that lift from the sea breeze and features like that that can initiate that isolated short-lived convection. And so that's mainly precipitation, and now we're trying to get into North Carolina though, because we got to remember our main goal here is to look at precipitation and how it affects hydrology in the state. And to do that, we're going to use North Carolina, which is conveniently already split up into 3 regions based on different characteristics. We have the geographic mountains region, where hopefully it's going to be steep terrain because they are mountains. And then we have the Piedmont, which is a bit flatter, and we have those clay soils there. And in the coastal plains, it's flat and wet and sandy. Those are important to keep in mind as we progress. And then these 17 river basins I mentioned earlier that we have split the state up into, they're conveniently somewhat situated in a main region, as you can see by the splits of these grays over the different watersheds and the river basins. So to get at this kind of relationship, this correlation and connection between precipitation and discharge, we want to apply the data set in a useful way, and we see doing that in a GIS framework as the best option, because that allows us to integrate all the data together and get some spatial information out of it. And so to do so, the first and most tedious and tasking and time-consuming process of this work was getting the data to work in GIS. And that involved taking the output from the algorithm and converting it to raster format. I guess what you need to know from there is that it eventually worked. And now we have all the data in raster format. So that step's done. Then it was gathering the USGS stream gauge data that we would actually use for, to look at our discharge from each of the river basins. Starting out, it looks like it's going to be pretty simple, and we're going to easily find the stream gauge that we want to use. However, once you limit this time frames to 4 years, 2009 to 2012, and once you only look at gauges that have discharge data, and once you only look at gauges that are right on the border where the main rivers exit the state of North Carolina, you're limited to these. And so these ones, these little green dots with black circles in the middle, black dots in the middle, these are actually the gauges we used to try to figure out what our regions we would use in this study are. And when I say that, what I mean is that we take this data that we have and we need to do watershed delineations. And that is kind of straightforward GIS processing that we do a bit of in advanced GIS. But what we do in this study is that we have to take an elevation layer. So we take an 80-foot DEM, or digital elevation model, from NCDOT. And to make it more accurate, this watershed delineation processing, to make it more accurate, we burn in a stream network. So it forces the DEM to know where streams are in North Carolina. After a little bit of magic, we finally define what the USGS stream gauge pour points are, or where do we want to know where the water is going. For example, these teal triangles represent stream gauges that were used. And so I define this as my area, or my point, that I want to know, okay, where is the water coming from that goes into this plant? And after defining that, we get final watersheds. And from all of the watersheds that we got from our previous stream gauges, I pulled out 5. And I did that because I wanted watersheds that represented each region of North Carolina, and I wanted watersheds that represented different characteristics across the state. Urbanization characteristics, just different terrains. And so in the end, we wound up with the French Broad and the Broad in the western North Carolina. We have the Yak and BD in central North Carolina, or the Piedmont. And we have the Neuse and Lumber, which make up more of the coastal characteristics of North Carolina. And before I go further into the actual results here, I want to touch on discharge and just some basics on discharge and how different characteristics can affect discharge. First off is basin size. How much water is being caught by the basin, how much is falling within the boundaries, and how long does it take for water to travel across the basin. Then terrain. How steep is the terrain? Because gravity does work, I promise, and therefore it accelerates things that go downhill. And so when the water falls in mountainous regions, it'll go faster towards the stream. Then we have soils. There's impervious soils like rocks or clay soils. And then there's pervious soils, which allow water to infiltrate the surface like sandy soils. Vegetation is another big factor because it causes for friction that helps slow the runoff and allows the time to infiltrate. But it also absorbs water, and we lose water through evapotranspiration. Then we have land use that is more commonly a human impact. Things like urbanization, the introduction of roads and roofs. So there's introduction of impervious surfaces that don't allow water to infiltrate and cause more runoff. And of course, weather. If it rains, then we'll get discharge. So looking at these different watersheds, I've selected these 5 main watersheds. What are their characteristics and how are they relating to discharge? These are my 5 watersheds. And rather than look at them all at once, we're going to go through one at a time a bit. First, I need to say these 2 are mountain watersheds. You can see by the little red boxes here. We've got our Piedmont watershed and our 2 coastal watersheds. Starting with the French Broad, the reds are developed areas and the yellows are more agricultural lands. The first thing we notice here is the main French Broad River runs right here, and right along the main river is a lot of development. Also, right along the main river and its tributaries are these agricultural landscapes. And agricultural landscapes are almost act similar to impervious surfaces by 2 ways. One, they decrease friction because we clear out the natural vegetation. And 2, we have compacted soils. And so it's harder for water to infiltrate. And so there's quite the concentration of developed agricultural right along the river. But in contrast, our other mountainous watershed, the Broad, is fairly natural landscape. There's very little development. There's a good bit of agriculture, but nowhere near like the French Broad. So that could have 2 different impacts on those 2 mountainous watersheds. As for the Yadkin, we have a good bit of development. It's a much larger watershed, as you can tell by the scale here, as compared to the previous scales. And what's interesting here is the distribution of agricultural lands. The whole watershed almost appears to be agriculture. And it's much further from the river, probably because in the mountains you need to be close to the river to actually get water, where here you can have really nice irrigation techniques. And so we'll see how that plays into it. And now looking at our coastal watersheds, they're very interesting because our lumber watershed is wet. There's a lot of wetlands, and there's very little development. And compare that to the Neuse, where we have Raleigh and parts of Durham and a lot of development, it'll be an interesting comparison throughout this. And another cool feature that you can see in these 2 watersheds is you can see almost the line of the Piedmont into the coastal plains, where it does cut through the region. So this region actually falls within the Piedmont, and then we quickly go into this more shrub and brownish area, which is typical of the coastal plain. Okay, so now we've got our data in GIS, we've got our stream gauges, we've got our watersheds. Now there's these things called zonal statistics, which are really neat, and one of the most useful things in this GIS work is that we can use these watersheds to pull out area-specific statistics. It works. So what we do is we take those earlier images of radar data, and we take our boundaries that we define using the watershed delineations. Putting those together, we're able to get those water-based statistics. So we actually say, okay, for this region, only take the data that falls within this region and calculate some sort of statistics. And that's very handy to do because it gets back at our research questions, which are looking at or how do the precipitation modes of organization vary seasonally and across North Carolina? And 2, how does that variation affect the regional hydrology of the state? So looking at our watershed-based statistics, this is some of the output. It's just in graphical format. And we're looking at, in the gold bars, is our isolated storms, those systems under 100 kilometers. Our purple bars are our MPF, precipitation contributions, those storms over 100 kilometers in scale. And we're looking at it by season, so winter, spring, summer, and fall. On our right here, this is just average daily precipitation, and what we already see are there's that very different, there's very obvious contrast in the differences between the modes of delivery across seasons. And this is similar to what we saw in the pictures and were concluding in the pictures earlier. But now we actually have some numbers to put to it. So in the winter, we can tell that MPFs dominate the total precipitation, where the total is this gray bar, just the summation of the MPF and the isolated. In contrast, the winter, especially for the mountains, is dominated by isolated precipitation. So similar to what we were seeing in those images earlier. However, the coastal is not dominated by isolated precipitation, but isolated precipitation still makes up about half of the total precipitation, whereas in the winter it made up negligible amounts. And we want to bring this back to our main goal of looking at how it affects regional hydrology. So our second research question there. And the first thing we need to do is get an idea of what does the discharge look like in each of the watersheds. And is there any kind of obvious response already between precipitation and discharge, like we would hope? And so this graph has a good bit. We're looking at in gold bars the MPF contribution to rainfall. In purple bars we're looking at that MPF contribution. In gold bars we're looking at the isolated contribution to rainfall, and those are up here. And down on this bottom x-axis is our discharge, just our daily average discharge. Now I need to point out this increases as you go up, whereas this bar increases whereas this axis increases as you go down. So keep that in mind. And first off, we're going to look at the mountainous watersheds. The French Broad and the Broad watersheds. The first thing that we notice is these seem very spiky, very flashy. And that is due to the steeper terrain and the rocky soils, which allow for more runoff. And what we're also seeing, if we look at a purple bar, is that it almost stacks right on top of a peak of that gray line, meaning that there's little time between when a rain event happens and we see a response in the discharge. And that's consistent with both of these mountainous watersheds. For the Piedmont, it's similar actually. Our Yadkin PD watershed, we see that it's still flashy, there's very steep slopes, and these bars with the purple bars and the gray lines, they seem to match up pretty well. So there's little lag between when a rain event happens and when discharge happens. This is a different story for the coastal watersheds. It's a much smoother appearance to that discharge. It's not as extreme of a slope. It's a more gradual slope. And if we try to match up these bars, it's a little bit harder to see which purple bar is directly associated with a peak in discharge. So that tells us that there might be a little more time between when a rain event happens and when we actually see the response in the discharge. All right, so we've been working through all of this. We've got our zone statistics. Now with all this information together, we can calculate some correlations between our precipitation numbers each day and our discharge each day. And what we are trying to get out of this is an assessment of the strengths of the correlations, but then also, is there a time lag between, or what is the typical time lag, if there is one, between when precipitation happens and when we see the response in the discharge. And that's what we're going to get at here in a bit. First off, we wanted to try to do it with the full data set, but you run into some problems. There's noise. We have a purple bar here, but then is this discharge or is this discharge? It's hard to tell which one actually matches up. And that noise in the data can contaminate our correlations. So we decided to go to an event-based analysis along with that full data set analysis, because this way we can get at the physical processes in a little bit more detail. We chose events where there was no rain before a strong rain event. Then the rain event happened, and within 14 days we saw a response in the discharge. And during that response in the discharge, there was little to no rain. And this just helps us narrow it down to more of the ideal events where we actually know that there should be some relationship or some correlation between them. So let's look at some of these correlations that we have. Keep in mind that it looks like there might already be a timeline. We see a peak in rainfall, so day 0, and then later on we see that response in correlation. That response in discharge. So here it looks like it might be up to 3 days, whereas here it might be day 0. We see a rainfall event and immediately response. In our coastal watersheds, it might take a little bit longer. And so is that what we're seeing? So keep that time lag aspect in mind. And we'll click through these, where this is the correlations between the mesoscale precipitation feature, and this is the correlations between the isolated precipitation and the discharge. Here are the correlation coefficients, so the strength of all our correlations. And the colors identify seasons, where dark blue is winter and lightest blue is fall. As we march through in time, starting off at day 0, so the rain event and the discharge are matched right on the same day, it's kind of hard to really pick out strong correlations. But then as we go to day 1, so we actually offset the data by 1 day, and so we have day 0, and then we wait and see, okay, is the discharge responding now after 1 day? It looks like that's the case in the mountainous watersheds. It takes only 1 day to get these strong correlations where we have something that looks like a correlation between the precipitation and the discharge. As we march to day 2, the Yak and PD, or the Piedmont watershed, starts to show that maybe this is the ideal time lag for how long it takes precipitation to make its way to the discharge stream gauge. As for the coastal watersheds, for isolated, for one thing, we don't see much at all right now, and we don't really see much for MPF. But as we march further in time, we start to see those correlations get a little bit stronger. This is suggesting that maybe by day 6, we're actually finally seeing that response in the discharge that came from the precipitation 6 days earlier. And you can march out further, it can even take up to maybe 9 to 10 days for these watersheds. Another thing to point out here is that, well, one thing, isolated seems to be much weaker throughout these different time offsets than the MPF correlations. And 2 is seasons are different. The timelines are different between seasons. In the news here in June, July, August, there's not as strong of a correlation as there is in September, October, November. So we need to look at that a little bit more and see what are these seasonal differences and why are they resulting, or where are they coming from. And so let's go to tables. It can be a little bit easier for this kind of information. Looking at the fringe broad starting out, it's fairly consistent. Our strongest correlations happen with single day offset. So when we say, okay, the rain happens now, let's wait a day and see if the discharge occurs, the discharge response happens a day later. Turns out that is the case for the majority of the fringe broad correlations. Same with the broad, with some seasonal differences. The Yak, we start to see a bit more seasonality in it. And then especially the lumber, we really see that seasonality where it may be, the best correlations may be 6 days after a rain event for the summer, but even up to 10 days for the winter time, you might need that offset. And the noose is the same, although it's important to point out for the summer and fall, and overall it typically is less of a lag time between a rain event and the discharge than we see in the lumber watershed. So we got all this information, we finally got all the data, now we need to make sense of it. And so that's what we're going to do here. Why are we seeing these differences in correlations, first off, between regions in North Carolina? Well, this is likely tied to past research and just based on watershed characteristics. Especially in the mountains where we see less of a time lag between the strongest correlations, and we see more of a time lag in the coastal plains, that's probably due to topography and the acceleration of the discharge down the mountainside. Also the soil composition, we have more water infiltration and therefore slower progression of the water into the stream network in the coastal watersheds. Another reason for this could be human-induced factors like urbanization. I say this because if we compare the lumber to the noose, the two coastal watersheds, the noose actually has a shorter timeline, which was interesting because the noose is a bigger watershed. Well, one feature that is very different between these two is the developed regions. There's much more development and more impervious surfaces in the noose, which may be enhancing and making that, and allowing that runoff to get to the stream network quicker which then leads to less of a time lag between rainfall and discharge. So those are two possibilities. And then how about that seasonality within watersheds? Why in the Neuse is it a 6-day offset in the summer where it's a 10-day offset in the winter? What causes those differences? Well, it could be the location of the rainfall. Here's a good example in the Broad. So in the Broad watershed, on the figure on the right, we have enhanced precipitation where these two circles are. These correspond pretty well with two reservoirs. Therefore, maybe the location of the rainfall is a player because we are getting the rainfall right into the stream network right away. It doesn't have to run off from anything. It's already there, and so we see that quick response in discharge. And now the last possibility, and what is more of what we were trying to look at here, is the type of precipitation, the characteristics of that precipitation. Is it MPF or is it isolated? And what we're finding overall is that the correlations with the MPF precipitation are much stronger than the isolated, and much clearer than the isolated precipitation. This touches on some past work. Well, I should first say, we kind of expected that isolated we would see a clearer signal because you're getting more intense rainfall over a shorter period of time, and so hopefully more runoff into the stream. However, past research and what this agrees with is that that's not the case. We actually have, it actually is more reliant on the total storm rainfall and the storm duration that actually enhances and relates and has better correlation with the discharge. And so this agrees with past literature, but a possibility is that it's also too low of a resolution. If we want to really get at the relationship between isolated convection and discharge, we may need to go down to maybe like a county level and to really see that correlation. And so pulling this all together, what we were trying to see are, does precipitation organization vary across the state? Does it vary seasonally? And then how does that affect discharge? Well, we've done that. We've created this data set to answer that question. We've applied the radar data set into a GIS framework. And we have found that there are variations of the precipitation regimes in the winter and fall. We've seen that variation across the state of North Carolina alone. And those variations potentially lead to a shorter time lag in western North Carolina and a longer time lag in eastern North Carolina. Other factors that play in are watershed characteristics, potential land use influences. But the one we're focusing on here, because that's what we're going for, is potentially the location of the rainfall and the type, MPF or isolated. And we're seeing that MPF makes the greatest contribution to the stream discharge and has the strongest relationships. And those relationships are typically strongest in the winter, spring, summer, and fall, when we have 80 to 90% of MPF precipitation making the total contribution. And in the summer, the relationships are weaker, where isolated systems are making that more of the contribution to total rainfall. So therefore, it seems like MPF precipitation is more substantial and more important when we're trying to assess stream discharge. It's looking at the MPF that has the strongest correlations. So what's this mean for people? It means, well, what we've gotten out of this is we have a better understanding of precipitation. By splitting it up by season and by mode of delivery, we have a better idea of what the precipitation is, what it looks like, and what are the characteristics of it. We can go from here and go to some more in-depth hydrological assessments. Now we've got this radar data in GIS format, so it can be picked up by a lot of new end users, like water resource management, emergency managers. It can be used in agricultural crop forecasting. There's a lot of new end users that can use this data now and apply it now that we have it in a more interdisciplinary format. And that's what I get to here. Now that we have this data in a GIS framework, it can be used outside more readily. It can be used outside the meteorology community more readily, and it can be applied to more real-world applications with more ease. And with that, I'll wrap things up. There's obviously a lot of people to thank, and I would like to acknowledge the help from Dr. Beta, Dr. Crawford, and Dr. Legend, who have been a huge help in getting the final product of this research.
All right, thank you, Chris. I want to open it up to general questions, just to let you know the format here. I'll let anybody ask the questions they want. The committee, Dr. Crawford, myself, and Dr. Pajeda will meet with Chris together afterwards, after the question session. And what else did I want to say? I'll just open it up. Anybody have any questions for Chris?
First question, then couple observations. When you did the, in the last part of your talk, you were looking at individual lags between precipitation events and your discharge response. I think that was good to look at that scale. I mean, when you're looking at 4 years, you can't really make those correlations. But in any case, what's the kind of the sample size that you were dealing with?
That's a good point, and sorry for the idea. Okay, so it actually ends up being almost less than 10% of the total data that had those ideal events. It changed across watersheds.
I mean, is it 5 or is it 20?
Well, it ranges from maybe 30 to 300 days. As for cases,
the individual storm events.
Oh yeah, individual storm events. So sorry, yeah, that ranges from about 5 to about, yeah, like you're saying, about 15 to 20.
Okay.
But some, like the lumber, it was hard to find some correlations because we did only have, for some seasons like the summer, we may only have had one ideal event.
Yeah. Then with your observation about the news, remember that you have at least a third of the watershed that's actually in the Piedmont.
Right.
Right. And in fact, where you define the outlet, it's probably more than a third. So that might affect some of your results. The other thing is when you were talking about the seasonality difference. You might consider that might have something to do with rainfall intensity, right? Yeah, summer precipitation. You have like a longer lag during the winter and a shorter lag during the summer, and you said that might
overall
be
is
the
also
location, but you might also consider that.
Like the storm intensity?
Storm intensity.
Yeah.
It's likely to be, you likely have more intense precipitation events during summer that would have some impact on that.
Right.
It depends on the scale of it.
No, I would definitely agree with that. And then also, I'd like to get your comment on this. I was also curious. This is something I did not go into, but maybe summertime evaporation. I don't know if that affects discharge much, because in your discharge, let me put
It has a huge impact on these kind of daily flows.
Yeah, in these images here, you can see that, like this is what got me pretty curious about it, is the fact that the discharge line really seems to putter out and settle down. It seems to, like, every winter is where, and spring is where maximums are, and then it kind of putters out in the summer. I didn't know if
that's evapotranspiration.
That is evapotranspiration.
And that's why you tend to have more floods in the spring.
Oh,
in the winter than you do during the summer. Maybe the bigger ones may be associated by tropical cyclones or something, but yeah, during the summer, evapotranspiration has a huge impact on the discharge. Yeah, I'm sorry, I'm going to have to
Okay.
be rude, but I'm late.
Well, thank you.
Nice job.
Thanks.
Other questions for Chris?
Well, Dr. Lecce, I think, kind of stole my thunder with one of my questions, so I had to come up with another one on the spot. How useful do you think this data set would be towards further breaking down to maybe different types of,
Yeah.
MPFs versus isolated or so forth?
As in, like types, as in.
Like you showed examples of coastal fronts versus mid-latitude cyclones or tropical or.
That's a great point, and that's something that I would love to see with future work on this. It would be tough to do for, say, like sea breezes. It can be picked out, that would be very time consuming, but something more simple would be picking out and matching dates with an existing climatology. So if there were a sea breeze climatology, that'd be really cool. But there is, and I think you're in the process of helping with this, a mid-latitude cyclone climatology being developed. And with that climatology, if we could match the dates of this data set with that climatology, then we could get a better idea of the precipitation structures within mid-latitude cyclones. And that would be really interesting and very useful for climate prediction purposes, because that would get at a better understanding of, okay, if this cyclone is coming from here, what is the typical precipitation pattern and characteristics of it? And knowing that, we can touch better on what we kind of expect for future climate precipitation prediction.
And where in the watershed the precipitation might fall.
Yeah. And then another step we'd like to do is matching with tropical cyclone dates. So we can see what of this precipitation is actually associated with this extreme tropical cyclones.
Cool. But there's a lot of year-by-year variability as far as that's concerned.
Yeah, exactly, which probably also influences the correlations a bit,
Sure.
which would be interesting to take out and redo.
Thanks.
Any other questions for Chris? Okay, Chris, thank you. Thank you. Let's take a short break. Maybe I'll reconvene here. Chris, you can pick it up in like, we gotta go pretty quick. It's presenting the time machine, about 5 minutes.
Okay. I didn't know we were being good. We're not asked a question. So what's the next question?
Want to play again today?
Sure. Yeah, I'd love to. It's still recording.
Oh, okay, thanks. Thanks, Tom. I'll see you later.
Nicely done, Chris.
Thank you.
Really fun.